Hello everyone. So in this video here, we will discuss another reaction of alkenes. Specifically, the reaction that we're going to be discussing here is the halogenation of alkenes. And then we will extend it to alkynes as well. So halogenation. Okay, that's the reaction that we're going to talk about. Now, what happens in this reaction? Okay, and this is coming from sections 8.9 and 9.8. Those are the sections that we're discussing here. Okay, what happens in this reaction is if you start with an alkene, the alkene is converted into an alkyl dihalide. Okay, it's converted into an alkyl dihalide. Now we've seen alkyl dihalides before, so once we get to the product, we will compare it to what we've seen before. Okay, so just to make sure that we are able to like differentiate these. Okay, so alkene becomes an alkyl dihalide. That is what happens here, and I'll come in and fill the specific nature of this dihalide after we've discussed the reaction. Okay, so we'll come and fill that in a bit. So schematically or pictorially, if we have an alkene, this reaction uses X2, where X is a halogen, So basically chlorine, bromine, iodine, any of those. Again, fluorination, we don't really do it like this. Okay, so no F2 here, but Cl2, Br2, I2, these are all fine. And another aspect of this reaction, which is very important, is that this reaction is done in a non-coordinating solvent. Okay, non-coordinating solvent. Examples of such solvents are chloroform, CHCl3, CCl4, or CH2Cl2. So these are polar, aprotic, and non-coordinating solvents. Okay, the halogenated solvents are mostly used for doing these reactions. So we need a non-coordinating solvent for doing these reactions. So again, since alkenes do addition reactions, things add to the alkene. We have the alkene here and we have X2. So the product that we get here is one where the halogens add to the two carbons that were previously part of the pi bond, of the double bond. Okay, so the pi bond breaks and the X breaks and it basically adds, although that's not what the mechanism is like, but that's how you would view it. Okay, so this sort of a substitution pattern, these are called vicinal dihalides. Okay, so vicinal is the term. Vicinal is when two substituents are on adjacent carbons, or if we generalize, positions essentially. So if two groups are basically adjacent to each other, then we call it a vicinal substitution. So what we make in this particular case, when an alkene reacts with a halogen, okay, is alkyl dihalides, and the specific nature of this alkyl dihalide is that it is a vicinal dihalide. Now, contrast this to what we've seen before. So I just want to review what we've seen before. Where did we see alkyl dihalides before? And it's always good to do this. So what we've seen previously is where you take an alkyne and you react it with two equivalents of HX, so a hydrohalogenation reaction, okay? So this is 2HX. When you do this, you get an alkyl dihalide, okay? In this case, though, both substituents are on the same carbon atom, okay? And this substitution pattern is called geminal, okay? So this is a geminal dihalide. So it is not restricted to halogens. It is basically open for any substitution pattern. So geminal is both substituents on the same carbon, okay? So that's called a geminal dihalide. So that means alkynes, when they undergo hydrohalogenation, we get a geminal dihalide. Alkenes, when they undergo halogenation, we got a vicinal dihalide. They're both dihalides, but they are not the same. One is a vicinal dihalide, another one is a the other one is a geminal dihalide. Okay, so that's the difference here. Okay, so this is the overall reaction now. So let's look at some examples and then we'll go from there into the mechanism and then discuss. Key thing is this reaction requires a non-coordinating solvent, okay? Because we will see at a variation where a coordinating solvent would change things, okay? So as an example to this, let's say if we start with something very simple, propene, and you do bromination on this, and you use chloroform as a solvent. So again, definitely memorize one of these solvents, reagent combinations, but you should be able to identify all of them, okay? So this, what we would get is bromine and bromine. Okay, so we get a geminal vicinal dibromide there, sorry. So we get that product. Now, it turns out if you do this reaction on a cyclic system, okay, so cyclohexene, if you do this reaction with cyclohexene, because we'll go into the mechanism after this, okay? When you do this reaction on the cyclohexene, we would expect, okay, sorry, something that I left out is this carbon here is chiral, so that means you're going to get a racemic mixture there. Okay, that's something to keep in mind whenever you get a chiral center, sorry, the carbon's a chiral center, so you have possibilities of enantiomers there. So when you have a cyclohexene and when you do a bromination on cyclohexene, okay, I think we have two possibilities here. We could have a possibility where the two bromines are cis to each other, okay? Now, whether they are on a wedge or a dash, we're basically looking at the enantiomer in this sense. But in this particular case, the molecule is also symmetrical, so it's a meso compound, so it should not have an enantiomer, okay? Its enantiomer is basically going to be the same molecule, okay? The molecule does not have an enantiomer. So we have a case where the two bromines are cis to each other, okay? We actually call it syn, okay? They're on the same side. Or the other possibility is that the bromines are anti to each other. That means one of the bromines is on a wedge and the other bromine is on a dash, okay? The other bromine is on a dash. So that would be anti. These are both possibilities because it is a ring, so they could both be on the same side, either pointing towards us or pointing away from us, or they could be on opposite sides. And it turns out that when you do a bromination, okay, your product is actually this anti-product. You don't get a lot of this syn product, okay? That's your product, the anti-product. So that means the mechanism that we come up with should be able to explain this halogenation. Okay, so that's something that we are going to add here. Important things to remember: anti-product is formed. So that means we get vicinal dihalides and they're also anti to each other. And that means even in this particular case, one bromine is on a wedge, the other one is on a dash, but because it is I think in this case we have only one chiral center, so it really doesn't matter, okay, whether it's on a wedge or a dash, because we have a racemic mixture. Okay, so this is a racemic mixture, but beyond that, the two bromines being on a wedge or a dash, that does not bring in anything additional. Okay, there's no additional complexity here. So what we'll do is we will try to come up with a mechanism of why or how do we get this anti-product. Okay, the mechanism should explain how the anti-product is formed. So we'll use this cyclohexene as an example. Okay, so what is the mechanism of this reaction? And the reaction we're working on is cyclohexene reacting with bromine in chloroform as a solvent. To give this anti-dibromo product. Okay. So the mechanism for that reaction starts with the cyclohexene. Alkene should behave as a nucleophile. Sorry, Br2. So this reacts with Br2. Okay. Now these are both bromines, they're both electronegative, but also remember that bromines are polarizable, okay, so they can develop del positive, del negative ends. So essentially what happens is the alkene is going to, the pi bond here does a nucleophilic attack on one of these bromine atoms. And that pushes away the other bromine as a bromide. And if that's the case, we would expect in this particular case to get a carbocation, okay? Carbocation. And let's assume that now in this particular case, since both carbons are secondary in nature, it really doesn't matter where I attach it. So let's say the bromine goes over there and the carbocation forms over here. And plus we have the bromide ion. Okay. Now, if this were to happen, or if this is how the reaction proceeded, okay, once this carbocation forms, I'm drawing out that hydrogen because I want to show some of stuff over there. Once this carbocation form, or once this carbocation forms, remember that the carbocation is trigonal planar. There is a p orbital that is here. So the bromide could now come and attack it from the top face, or it could go and attack it from the bottom face, or like from the front or from behind in some sense. And that means we should be getting both the syn and the anti-products. But what we get is only an anti-product. We don't get any of the syn products. That means in this particular case, the structure that we are working with, somehow this front side attack okay, the front side attack, which would give us the syn product, that's somehow prohibited, okay, that's somehow blocked. But if it is a carbocation, that attack should not be blocked, okay. And so what that tells us is that there's probably no carbocation in this mechanism, because if there were a carbocation, it should give you both syn and anti products. So there is no carbocation in this mechanism, okay. So I'm going to redo this. Instead, what happens is, when the olefin, okay, when the pi bond attacks the bromine, the other bromide gets kicked out, and at the same time, notice the bromine has 3 lone pairs on it. What happens is, as this attack happens, one of the lone pairs on the bromine, that comes and attacks the other carbon back, okay? So it's like, so what's going on here is the pi bond attacks one of the bromine atoms. Okay, the pi bond attacks one of the bromine atoms. The other bromine gets kicked out as a bromide, and simultaneously a lone pair on the bromine which was attacked comes back and attacks this carbon, the other carbon. And so what we get is a structure like this. Now this bromine here should have 2 lone pairs to it, and that's too many bonds, not too many, like that's more bonds than what we've usually seen a halogen do. And so this bromine here is positively charged. We call this a bromonium ion. So it's the carbocation equivalent of a bromine bearing a positive charge in some sense. I think very crude. It's not a carbocation equivalent because this should be sp3 hybridized at this point. It's not sp2 hybridized. So it's not in terms of charge. Okay, that's what I meant. It's the equivalent of a carbon bearing a positive charge in some sense. So bromonium ion. So it's a so like the carbocation, you know, something like that. So so we get this bromonium ion. Now, when this initial attack of the olefin happens, also realize that the carbons that are part of this pi bond, they are also sp2 hybridized. That means they are flat. And the pi bond has one lobe that's above and one lobe that's below. Or in this particular case, there's one pi cloud that's in front and there's another pi cloud at the back. So both pi clouds could go and attack the bromine. Okay, both pi clouds could go and attack the bromine. And so we could have a bromonium ion where the bromine is on a wedge, or we could have a bromonium ion where the bromine is on the dash. Okay, so that's another possibility. So we could get this, or we could have a bromonium ion where the bromonium ion is on a dash. Okay, so they are both possibilities. We'll go with this for now, okay, but they're both form. They both form, and it's almost like enantiomer thing. So it's like a racemic mixture at this point in some sense. But again, there's plane of symmetry, so that kills things, but that's what we're looking at here, okay. So we get this bromonium ion. Now, because we get this bromonium ion, and it is actually, because it's on a wedge, it's sitting here, okay, in front of the molecule, somewhere here. So because it's a bromonium ion, what that does is it blocks this face of the double bond, or the carbons that were previously double bonded to each other. It just basically blocks this front face. And so for the bromide, the only option is for it to go and attack from the back, because the front is already blocked. And when it goes and attacks the back, and in this particular case, again, both carbons are equivalent in terms of their degree, like secondary. They're both secondary, or in this case, they might look like tertiary, okay, because they're both equivalent. Okay, it doesn't matter where the attack happens, but the bromide is going to attack from the backside, and at the same time, this bond breaks up from that side to give the lone pairs back to the bromine. And so what we would get is bromine on the dash here. This opens up, the bromonium ion opens up, and that gives us a bromine on the wedge at the bottom. Okay, so we get a dibromo compound which is anti, okay, because they are both anti or trans to each other. So the bromonium ion therefore explains the formation of this anti-product. Now, this bromide could have as well attacked this carbon here, and then the bond would have opened here. That would have given us the bromine on a wedge at the top and the bromine on the dash at the bottom. Okay, so we get that product. Now, so that explains how these anti-products are formed. And plus again, these are both chiral centers now. That means we are going to get racemic mixture here. Okay, this is a racemic mixture because it's not a meso compound now. There's no plane of symmetry. So this will give us a racemic mixture. And it kind of starts out here because we could have made two bromonium ions. Those were enantiomers or enantiomeric to each other, but it's a meso compound again. Okay, so that would give us the anti-product. So that explains, the bromonium ion explains why we get this anti-stereochemistry. Okay, so that's the mechanism of a bromination or a halogenation in general. So now let's go ahead and look at a few examples. And I want to choose a specific example here where we have a double bond, and now we have an alkene that's kind of this is not the carbons are not equally substituted. Okay, this carbon is disubstituted, that carbon is tri-substituted. Or if we just look at the two carbons that are part of the pi bond, this is mono and that's disubstituted. There are two substituents coming out of that carbon. Okay, so in this particular case, again, when we do the reaction with bromine, now it does not have to be bromine. Okay, we can do a chlorination. I think brominations and chlorinations are the most common halogenations that are done. People don't do iodonations or fluorinations. Okay, when we do this, what we are going to get is a dihalide where the two chlorines are anti to each other. Okay, one chlorine is on a wedge, the other chlorine is on a dash, and again we have chiral centers, so that means we will get plus minus. Okay, so the racemic mixture is what we're getting here. So we get those two products. Now I want to quickly go over the mechanism here to highlight something which is not very evident in this particular example, but it is important in something that's going to follow. Okay, so in this case, if we work on a mechanism, and I think it is good practice anyways, so if we work on a mechanism here, I'm going to write the chlorine like that. So the pi bond goes and attacks one of these chlorines. The other chlorine gets pushed out, and at the same time, a lone pair on that chlorine comes and attacks the pi bond back. Okay, it comes and attacks that other carbon, not the pi bond, attacks the other carbon, because once the first attack is happening, this carbon should already keep, or actually in this particular case, I think I'm a mistake here. I'm going to fix it right away because it is unsymmetrical in some sense. Okay, so the pi bond opens up and attacks the chlorine. Okay, when that happens, the other chloride is going to get kicked out, but also think about where the carbocation would form. The carbocation would form at the more substituted carbon. Okay, so that's where the positive charge is developing. And as this happens, a lone pair on this chlorine goes and attacks that carbon, which would have become a carbocation had there been no electrons here. Okay, so that goes and attacks that carbon, and so we get an intermediate here. So that carbon was sp2 hybridized, now that becomes sp3 hybridized. So the methyl, let's say, becomes on a dash. It could be on a wedge, depending on the situation, or depending on the other scenario that you could draw. So the chlorine now has two lone pairs. It has a positive charge to it. So you've made a chloronium ion. Okay, you make a chloronium ion. And plus you have chloride. Now in this particular case, you have two carbons that can be attacked by this chloride, and you might think that this carbon is more substituted, this is less substituted, and since the chloride comes from the back, it would probably attack the less substituted carbon. But no, in this particular case, we have this chloronium ion, which has this positive charge, but the halogens, they are not really good at holding that positive charge. They are bigger atoms, they don't want to do that. So, and plus, so what happens is this positive charge actually imparts some carbocationic nature to these carbon atoms, which are connected to that chlorine. Okay, they both have some positive charge on them. And since this is the more substituted carbon, this would have a bigger del positive, meaning it has a bigger share of that positive charge. And this being a secondary carbon, or this being the less substituted carbon, it's going to have a smaller share of that positive charge. So when the chloride comes and attacks, it actually attacks the carbon which has a higher del positive from the backside. Okay, and then this electrons, that bond becomes a lone pair on the chlorine. And so what we get here is a product where the attack is happening from the backside. So the methyl, which was on a dash, now ends up on the wedge, or now comes on a wedge. The chlorine came from the backside, so the chlorine is on a dash over there, and this chlorine is on a wedge here. So we get that product that we have. Now, because initially the chloronium ion could have formed on the backside, you would also have its enantiomer possible. So that's how this reaction works. So the attack in a chloronium ion happens at the more substituted carbon, okay, because that has a higher carbocationic nature to it. Okay, so that's the mechanism. That is the product that we would expect. Now, in this particular case, as I said, it really doesn't matter. They are both chlorines, but we will see in a follow-up reaction that, you know, it really matters. Okay, so that's the halogenation reaction. I think we can look at another example. This is from the textbook. Okay, so when you start with this alkene here, and you do, let's say, a chlorination on it. You're going to get chlorine, chlorine, plus chlorine, chlorine. Okay, they're both enantiomers of each other. If you start with the trans alkene, sorry. If you start with the trans alkene, you could get chlorine, and chlorine. And this product now, and you might think you will get another enantiomer, but if you look at this compound here, once I do a rotation about this bond, I can draw it like that, which now is a meso compound. Okay, so when you have more than one chiral center in your molecule, there is a lot of stereochemical aspects that you have to keep in mind. Okay, so that will be an example, another example of a chlorination. Okay, this is alkenes. What would happen if we did this on an alkyne instead? Okay, so alkynes, when you do chlorination on them, they will become vinyl dihalides with X2, okay, or you take alkynes and do the reaction with excess of halogen, then you get alkyl tetrahalides. You get an alkyl tetrahalide. So now four halogens there. And now in this case, when you have a vinyl dihalide, E-alkene is major. Okay, that's the major product. I will show you examples of both. So essentially what we're saying is, and this is always simple once you understand the alkene part, then the alkynes are always simple. So essentially what we're saying is, if we had an alkyne like this, you react this with X2, they're going to add to this double bond, or triple bond, sorry. And what you would get is this is our E product plus we will have our Z product, and the E product or the E stereoisomer is our major product. But if you took the same alkyne and if you reacted it with two molecules of a halogen, which could also be read as excess halogen, then you're initially going to get the E and the Z, and they will add another molecule of the halogen. Okay, so in the end, what you would end up with is X, 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 and X. You will have four halogens. And the way you get here is when both of those products, they react with another X2, essentially another halogen, that gives you this tetrahalide. So this is an alkyl tetrahalide. This is a vinyl dihalide because the halogens are both connected to carbons that are part of a double bond. So they're vinyl dihalides. So you get E and Z. But again, I think for our purposes, we'll be focusing mostly on this excess reaction. I don't think we will be talking about those much, okay? So the alkynes would give us these products. And in this particular case, there is something like a chloronium or a halonium ion that's formed. That's why we get the E product as the major product. But when you get to a tetrahalide, there is no stereochemistry here. We don't have to worry about cis and trans or anti and syn. So there's none of that here. Okay, so that's the halogenation reactions. Please practice some examples and it should be easy. We will do a follow-up to this video, which is on a related reaction to the halogenation reaction. Okay, bye.